Welcome back. In the last lecture, I introduced ammonia water systems and we discussed the properties of binary mixers of ammonia water. This lecture is a continuation of the earlier lecture, and in this lecture I will discuss in detail the working principle of ammonia water systems. So, the specific objectives of this particular lesson are to explain the working principle of absorption systems using ammonia water pair with some of its salient features, explain the principle of rectifying column, discuss briefly the steady flow analysis of the system, explain the principle of triple fluid absorption systems, and finally compare absorption and compression refrigerant systems. At the end of this lesson, you should be able to explain the working principle of ammonia water system and its salient features, explain the operation of rectification column with enthalpy composition diagrams, perform steady flow analysis of the system, explain the basic principles and features of pumpless triple fluid systems, and finally compare compression refrigerant systems with absorption systems. So, let me give a brief introduction. Absorption refrigerant systems based on ammonia water, they are one of the oldest refrigerant systems which were developed at the end of 19th century. These systems can be used for both refrigeration and air conditioning applications because the ammonia is the refrigerant here, so it has a very low freezing point and you do not have the problem of like in water where it cannot be used for sub-zero temperatures. And these systems are available in very small refrigeration capacities to very large refrigeration capacities, and mainly they are used in domestic refrigerators in pumpless form and also in large cold storages. Now, the operating pressures in ammonia water systems are much higher than atmospheric. So, you do not have the problem of air leaking into the system. This is one of the typical problems of water lithium bromide systems which operate under vacuum. So, you always have air leaking into the system. This problem is not there with ammonia water systems. And you also do not have the problem of crystallization, which was again a typical problem with water lithium bromide systems. However, ammonia is not compatible with materials such as copper or brass. So, normally the entire system is fabricated out of steel, and ammonia is both toxic and flammable. So, we need to take certain safety precautions while designing and operating these systems. Now, let me explain the operating principle. Major difference between this system and water lithium bromide systems is that you use 3 additional components here, and these 3 additional components are a rectification column, a deflagrator and a subcooling heat exchanger. Without rectification, vapor leaving the generator may consist of 5 to 10% of water, and the need for rectification was explained in the last class. If you do not rectify the vapor, you have 5 to 10% of water in the refrigerant circuit. This will create problems like non-isothermal condensation and evaporation, and it will also increase the evaporator temperature. It increases the circulation ratio. So, ultimately the system performance suffers. So, in ammonia water systems they have to be designed in such a way that most of the water is confined to the solution circuit only, and in the refrigerant circuit you have almost pure ammonia. So, this requires the use of a rectification column. Okay, and the rectification column consists of the generator, a rectifying column and deflagrator. So, this is something different from water lithium bromide systems. Okay, and what is the function of subcooling heat exchanger? The subcooling heat exchanger is used to increase the refrigeration effect and also to ensure that only liquid enters into the refrigerant expansion valve. Now, let me explain the operating principle. Okay. So, as I mentioned, you have the for basic components here, you have the evaporator, condenser, absorber, solution pump and generator. In addition to these basic components, you also have an additional heat exchanger here, a subcooling heat exchanger, and you have what is known as a deflagrator here, and you also have a rectifying column. Rest of the components are similar, like your solution pump, expansion valve, liquid suction heat exchanger. All these components are similar to water lithium bromide systems. So, the working principle is like this. Let us begin with point 14, which is nothing but the exit of evaporator. So, at this point you have low temperature, low pressure refrigerant vapor. This low temperature, low pressure refrigerant vapor enters into the heat exchanger 1, where it exchanges heat with the refrigerant liquid coming from the condenser. In this process, the refrigerant vapor gets superheated and the liquid gets subcooled. So, this is something similar to your liquid suction heat exchanger used in vapor compression refrigerant systems. So, okay, so what comes out of the heat exchanger is a superheated vapor still at low pressure. So, this superheated vapor now enters into the absorber. In the absorber, it comes in contact with the weak solution coming from the generator. So, this is your weak solution. Okay. Weak solution here means weak in refrigerant. So, this weak solution and ammonia vapor coming from the evaporator, they come in contact in the absorber and the refrigerant is absorbed in the absorber. Since this is an exothermic process, heat is rejected in the absorber, and what you have at the outlet of the absorber is a strong solution at 0.2. Okay. So, at 0.2 you have a solution that is rich in ammonia. Okay. This is still at low pressure. So, this strong solution is pumped to the generator pressure using a solution pump. Okay. So, in the solution pump it is pressurized, and this high pressure solution, which is still at low temperature, enters into this heat exchanger 2. Okay. In the heat exchanger 2, this is nothing but your solution heat exchanger, where it exchanges heat with the hot solution coming from the generator, that means at 0.6. Okay. In this process, this strong solution becomes preheated. So, it comes out at higher temperature. So, temperature at 0.4 is much higher than temperature at 0.3. So, this preheated strong solution enters into this rectifying column, and in this rectifying column this strong solution falls through this rectification column, and it ultimately comes to the generator, where you supply the heat, and because the heat supply, vapor is generated, and this vapor gets rectified in the rectification column and deflagmator, and finally what you have at the exit of this deflagmator is almost pure ammonia, that means almost about 99.9% ammonia. Okay. So, this 99.9% ammonia vapor, which is at high pressure and high temperature, goes to the condenser. It condenses in the condenser by rejecting heat of condensation QC to external heat sink, and it becomes a high pressure liquid 0.11, and the high pressure liquid at 0.11 now flows through the heat exchanger, where it rejects heat to the vapor coming from the evaporator. So, in this process it gets subcooled. So, at 0.12 you have subcooled refrigerant liquid still at high pressure. So, this subcooled liquid refrigerant at high pressure is expanded in this expansion valve, and the resulting mixture of liquid and vapor at 0.13, which is now at very low temperature and low pressure, enters into the evaporator. It takes the heat from the refrigerated space, provides the refrigeration effect QE, and in this process it becomes a vapor, and this vapor goes back to the heat exchanger, and that is how the refrigerant circuit is completed. Now, coming back to the solution circuit, in the generator refrigerant vapor is removed from the solution. So, what you have at the exit of the generator is a weak solution 0.6. So, the weak solution at 0.6, which is quite hot and which is at high pressure, now flows through this solution heat exchanger, where it gives off heat to the strong solution coming from the absorber. So, in this process the temperature of the weak solution reduces from T6 to T7. Still, since this is still at high pressure, its pressure has to be reduced to that of absorber pressure. That takes place in this solution expansion valve. So, at the exit of the solution expansion valve you have low pressure weak solution, that is 0.8. This low pressure weak solution now comes in contact with the refrigerant vapor coming from the evaporator, and absorption takes place, and that is how the solution circuit is completed. So, this is the working principle of vapor ammonia water system, and this is actually you can call it as a single stage ammonia water system. Okay, this is a typical system used in most of the commercial installations. Okay. So, the analysis and analysis of this system I will explain a little later. Before coming to the steady flow analysis, let me explain the working principle of the rectification column. This is the rectification or the rectifying column, which consists of the three components, and let us first concentrate on this rectification column. Before explaining that, I forgot to mention one thing. In the deflagmator, the refrigerant vapor rejects some of the heat to a heat sink. That means some heat rejection takes place in the deflagmator. That heat rejection is given by QD, and due to this heat rejection, some of the solution condenses in the deflagmator, that is known as reflux. Okay, so I will explain this while explaining the rectifying column. Okay. So now let me just summarize the energy flows into and out of the system. We have seen that high temperature heat input is given to the generator QZ, and low temperature heat input is given to the system at the evaporator. This is nothing but your useful refrigeration effect QE, and then heat rejection takes place at absorber, condenser and deflagmator. Deflagmator is a new component here, and a small amount of work input is required to run the solution pump. So these are the typical energy flows into and out of the system. Now let me explain the principle of rectification. So as I explained already, the rectification system consists of generator, a rectifying column and a deflagmator. So let me show the schematic of it. So you can see that the whole thing is your rectification system. It consists of 3 components: generator, and this is your rectification column, and a deflagmator. Deflagmator is at the top of the rectifying column, and heat is supplied to the generator. High temperature heat QZ is supplied to the generator via a heating medium. So because of this, vapor is generated. Okay, so vapor is generated and vapor moves up. This vapor comes in contact with the strong solution coming from the absorber. Okay, so there is a direct contact between the strong solution and the vapor in this lower portion of the rectification column. As a result, we will see that this vapor becomes rich in ammonia. That means by the time this vapor comes from this point, the lower portion, to this point, it becomes stronger in ammonia, and further enrichment takes place in this column, where the vapor comes in contact with a reflux that is coming from the what is known as the reflux condenser. Sometimes the deflagmator is also known as reflux condenser. Reflux condenser. So in the reflux condenser, what happens is some heat is taken out of the hot vapor by using a cooling water, and during this process some of the vapor condenses. That condensed vapor is called as reflux, and due to gravity this falls down, and as it falls down it comes in contact with the vapor that is moving up. That means the descending liquid comes in contact with the ascending vapor, and during this process further enrichment of the vapor takes place, and ultimately what you have at the exit of the rectification system is almost a pure ammonia. That means, as I already mentioned, you have about 99.9% ammonia in the vapor. Okay, it's almost pure ammonia. Okay, so in order to achieve this, you have to design the rectifying column properly. Now let us concentrate on each component. That means the lower portion of the rectifying column, and let us see how what is the working principle of this and how do we show this on enthalpy composition diagram. Similarly, we will look at the upper portion and explain the working principle and show this on enthalpy composition diagram. Okay, so as I said, you have seen that rectification system consists of the 3 components, and a heating medium supplies the required heat input, as I have already mentioned, to the generator, and heat QD is rejected to the cooling water in the deflagmator. Okay, so at one place you supply a high temperature heat, at another place you reject some of the heat. Now let us look at the generator plus lower part of the rectification column. Okay, first let me show the working principle. Okay, so you can see here the generator here. This is generator G, and this is the lower portion of the rectification column. Okay, so you have in the generator you have you have a solution of ammonia and water. Okay, and from the top strong solution of ammonia is coming from the top. Okay, so this is what is coming from your absorber. Okay, and heat is supplied to this solution bath at the bottom portion. You are supplying the heat to the solution here. As a result, vapor is generated. So this is the vapor moving up, and vapor has a initial concentration of zeta WV. Okay. So, this vapor moves up, and as it moves up, it comes in contact with the liquid that is coming down. Okay. The liquid is coming down, and remember that this liquid is much cooler, and it is coming from the solution heat exchanger. So, its temperature is always lower than the vapor temperature. So, the hot vapor comes in contact with the strong solution in this column. Okay. What happens then? So, you can see this in the enthalpy composition diagram. This is the state of the vapor at this point. Okay. State of the vapor at this point. Okay. That means at the lower portion of the rectification column. This vapor comes in contact with the solution that is entering into the rectification column. And what is the state of the solution that is entering into the rectification column? That is this. Okay. So, that you can see that there is a temperature difference between the vapor and the solution, and the vapor is much hotter than the solution. As a result, heat transfer takes place from the vapor to the solution, and in this process the temperature of the vapor reduces and the temperature of the solution increases. Simultaneous to heat transfer, you also have mass transfer. Okay. How mass transfer takes place? When heat is supplied to the solution that is coming into the system, some ammonia vapor is generated. Okay. That means ammonia is generated from the solution, and this ammonia vapor will be mixed with the vapor that is moving up. So, you can see that as the okay. So, as the vapor is moving up, its state is shown by this arrow here. That means it becomes progressively rich in ammonia. So, okay, so you can see that its concentration varies from this point to this point. That means it gets enriched in ammonia, and at the same time its temperature drops because of the heat transfer. Simultaneously, what happens is, since you are stripping this solution of ammonia, obviously its concentration has to drop. So, you can see that its concentration is decreasing in this direction. Okay. That means the vapor concentration increases in this direction and the solution concentration decreases in this direction. Okay. So, the net effect is that the vapor becomes rich in ammonia and the solution becomes weak in ammonia. Okay. So, that is what is shown in this process. Okay. How the temperature increases, and if this rectification is perfect, you will find that at this point the strong solution that is entering into the system will be at equilibrium with the vapor that is leaving the system. That is what is shown here. Okay. So, this solution this vapor is at equilibrium, this liquid is in equilibrium with vapor that is leaving the system. Okay. Of course, in actual case this is not possible, because for perfect rectification and perfect equilibrium you require an infinite column. So, in an actual system you will find that there is no equilibrium is not there. Okay. One advantage of this particular system is that you can see that some of the heat is transferred from the hot vapor that is coming from the generator. Okay. And this heat is given to the solution that is going to the generator. That means the solution that is going to the generator is getting preheated by extracting heat from the vapor. Okay. This is beneficial because obviously this will reduce the required heat input in the generator. Okay. Otherwise, if, let us say that if this is not there, then it has the entire heat has to be supplied by the external medium in the generator itself. Okay. And this is wasteful, because ultimately the vapor has to go to the condenser, and the heat will be rejected in the condenser to a low temperature heat sink. Okay. So, instead of throwing it to the low temperature heat sink, you are extracting some of the heat from the vapor before it goes to the condenser. Okay. So, this is good as far as the system COP is concerned. Okay. So, ultimately what has happened in this particular lower portion of the rectification column and the generator is that there is an exchange of heat and mass between the vapor and the liquid. Okay. During this process, vapor becomes hot and it becomes weak in ammonia, and the liquid becomes hot and weak in ammonia, and the vapor becomes cool and rich in ammonia. Okay. Okay. So, that is what I have summarized here. Heat and mass transfer take place between the ascending vapor and descending liquid, and ascending vapor is enriched in ammonia and descending liquid becomes weak in ammonia, and in an ideal case vapor leaving will be in equilibrium with liquid entering. Solution entering the generator is preheated. So, this is beneficial as required heat input is reduced. Now, let me explain the deflegmator or reflux condenser. Okay, so this shows the upper portion of the rectification column plus the deflag as you know that this is the deflag D. Okay, what is happening in this one, the vapor that is entering into the deflag is nothing but the vapor that is leaving the lower portion of the rectification column. Okay, so that enters into the deflag and let us say that it moves up, and at the upper portion it rejects some heat to the low temperature heat sink. Okay, so this is the heat reject